core topics here at the university and especially in our institute. So today we will learn a lot of what Niklas and I are actually doing as regular work when we're not doing lectures. So we start with the learning goals once again. So after this lecture, you should be able to describe the pros and cons of centrifugal microfluidics. You should be able to understand the driving forces, so all the forces that are relevant in microfluidics, in centrifugal microfluidics. And finally, you should also be able to understand some of the basic unit operations that are regularly applied in centrifugal microfluidics. So let's start with the motivation and the idea. So on the right-hand side, you can see a microfluidic cartridge, which was developed by one of my colleagues here at the institute. And this is really the basic design that you often see in centrifugal microfluidics. So it resembles to a disc that you probably know from DVD players, or if you're a little older like me, from CD players. And the fluidics are those chambers depicted here on the cartridge. The main idea of centrifugal microfluidics is that you use the centrifugal force field to transfer liquids or to transport liquids along these structures. So if you now compare this with the concepts that Niklas presented last time, what could be a consequence, what could be an advantage if you think about this idea of transporting liquid? Any ideas? Yeah?
There's no need for pumping the liquid?
Right. So that's one of the biggest advantages that there is. So one of your friends has said that you don't really require pumps. And that's the main advantage that you have. So in principle, you can just inject liquid, press start, and then your protocol runs. And you don't have any tubings or channels that connect your cartridge to the external pumps. A second thing that comes along with this principle of the centrifugal force transport is that you are able to build monolithical cartridges. So what does this mean? You can basically, yes, so it's really the contrast to what Niklas presented last time, that you have this PDMS chips which need to be pushed onto class chips and so on. And here it's really, you have a chip, you manufacture it like it is here, based on a PDMS mold, and then can seal it with a simple foil, adhesive foil for example. And this is that's the reason why you can simply throw away the chips when you don't really need them anymore. Okay, so then let's look a little more into this platform idea of the centrifugal microfluidics concept. So on the right-hand side, you can see one of the devices that was always sold by one of our spin-off companies. You see that there's a cartridge that you usually put into this device, and then the automation procedure starts. And like I already said, so the main control parameter is the spinning frequency, and as is depicted in this graphic down here, the spinning frequency can be modified. So sometimes you spin at a high frequency, sometimes you spin at a low frequency, and by varying the frequency, you are able to do the unit operations. A second parameter that is really important is the temperature. Do you have an idea why this is of importance? Incubation? Yeah. So I mean, the incubation, that's one part why it's important. And so if you want to say it or state it more general, most of the time we do biological applications on our cartridge. And there you often require temperatures to work with your enzymes. And so, for example, if you want to do a SARS-CoV detection, you have to do a PCR. And for the PCR, you obviously also need some temperature steps that you have to control. Okay. So once again, if you look at the picture on the right-hand side, one big advantage is that it is very easy based with the interfaces. So if you think back to the last lecture, where you've seen pumps and then you had lots of tubes that connect your pumps with your chip, that's not really what you require when working with centrifugal microfluidics. So a second advantage that I haven't mentioned in the previous slide is that you don't really have issues with gas bubbles. So why is that? Do you have an idea why this is not really of importance in centrifugal microfluidics? Okay, so maybe think of centrifugal microfluidics as a gravity field. Okay, so one of the guys who joined us online says that they are lighter, so they won't migrate as fast. That's almost, that's very close. But let's say, let's consider a very big chamber, and you have liquid inside, and you have some bubbles, some air bubbles. And you now have a centrifugal gravity field, which is proportional to the rotational frequency. So what would happen with those bubbles? Would they stay in this position?
Move or reverse.
Sorry?
It will move or reverse.
So they will move definitely, and you can think of it, the centrifugal force field is basically similar to gravity, just much more stronger. And in the case of gravity, I mean, everybody of you would know what would happen, right? The density is different, and the liquids or the gases with lower density will migrate to the top. That's what you see daily. If you have water with bubbles inside, the bubbles move into the direction or in the opposite direction of the gravity field. And the same thing occurs in centrifugal microfluidics, except that we have way stronger gravity forces. And that's one of the big advantages. So you can easily control the position or the movement of the bubbles by making use of the centrifugal gravity field. And the last point, and that's really maybe the application point for the centrifugal microfluidic platform, is that you can use it for point of care diagnostics. So all those points, easy interfaces, no issue with gas bubbles, easy cartridges, that makes it really suitable for this point of care scenario. And like I said at the start, at the right hand side you can see a device or an instrument from one of our spin-offs, and they developed the SARS-CoV test for point of care, so for a clinical setting. And I will come back to this later, and we'll have a closer look at the cartridge that they developed. Okay, but let's first start with the forces and the physics of centrifugal microfluidics. So, you probably are familiar with centrifugal forces in general because you had it in some kind of mechanics lecture. And you probably know that there are lots of pseudo forces in rotating systems that you can describe. And obviously the most important one in this context is the centrifugal force itself. But there are also two other forces, the Euler force and the Coriolis force. Each of them depends on different parameters and variables. So what you can see here, the centrifugal force, it depends on the rotational frequency, it depends on the mass. So that's basically what we've seen with the bubbles before. So the density is and the volume are part of the mass. And it depends on the radial position. So if you look at the equation, you have, I can show it in slides. So the faster you rotate, the stronger your centrifugal force will get. And the further radially outward you are, the stronger the centrifugal force gets as well. So then there's the Coriolis force, which is mainly known from the flows that if you look at the weather and you want to understand why there is a high and there's a pressure low area, so usually the Coriolis force plays a big role in there. But yeah, it's also important for the smaller applications for the microfluidics. If you look at the parameters, you have the mass again, you have the rotational frequency, and you have the velocity of your mass. So in terms of, if you compare it to the centrifugal force, the order of magnitude of the Coriolis force is much less than the centrifugal force. But it can still be used for some minor unit operations, so you can do switching by using the Coriolis force, or you can do mixing by using the Coriolis force. And the last force is the Euler force. So once again, you have the mass and the radial position, and you have the acceleration of the rotational speed. So the idea is, you can imagine it like that, if you really rotate, for example, if you rotate the disk very quickly back and forth, there are Euler forces, or there exist Euler force on the disks, because you just change or you use the acceleration effect back and forth again. And we will have a look at what happens with liquids when you make use of this Euler force in the unit operations section later on. So that's it for all the forces that are coming from the centrifugal microfluidics part. And now I want you to think back about what you've learned this semester, because there are other intrinsic forces that are important for when working with centrifugal microfluidics, and there are other extrinsic forces that are important. So once again, intrinsic in this case means the forces that are just there, that you have to handle with or that you have to work with, and the extrinsic forces are usually external forces where you make use of an external actuator, for example. So yeah, I want you to take, let's say, 1 or 2 minutes and think about, especially when looking at the topics that we had, which forces play an intrinsic role in centrifugal microfluidics and which forces play an extrinsic role in centrifugal